So, good morning. So, in today's lecture we will start little bit about the fundamentals of quantum mechanics. So, now you should understand that we are not teaching quantum mechanics as a course. So, it is only a very small portion of the nanoscale energy transport. So, I will give you a very brief overview, solve one or two examples, and then try to see where quantum mechanics is applied in the context of nanoscale energy transport. So, since till the end of the last lecture, we have looked into an introduction about the nature of the microscopic energy carriers, the classification, and also the looking at the contribution of different energies, the kinetic energies. If you look at translational, rotational, vibrational from the classical perspective and from the quantum mechanical perspective, right. So, from the classical perspective we can directly derive these energies, okay, from our knowledge of classical mechanics. From the quantum mechanical perspective, I have given down the expressions, okay, right. I have stated the expressions for the energies, corresponding energies for translation, rotation and vibration, all of them here. Okay. So, these are the things that we will be deriving now in the next few lectures, because you should understand that when we talk about the really nanoscale energy transport, okay, where the the wave effects become dominant, we have to define these energy states based on quantum mechanics, right. So, that is why we need to understand a little bit. We are not we are not taking a separate course only on quantum mechanics to go into all the nitty-gritty details, but just a broad overview, because we are engineering students. So, we should just understand the basic concepts and how from there we go into statistical thermodynamics. Okay. So, beyond that it is not of our concern. So, now when we talk about where the quantum effects are to be felt in the nanoscale regime. So, I will just give you once again example where we have, for example, a thin film of some semiconductor material. Let us say it could be germanium or silicon. These are the most commonly used semiconductor materials for building devices. Okay. So, now this film could be of the order of say several 100 nanometers to ranging to of the order of 1 nanometer say. So, let us say 1 nanometer to say several 100 nanometers, okay, or let us say 1000 nanometers. Okay. So, now you have a heat transport across this thin film. Okay. On one end you have a higher temperature, the other end you have lower temperature, and therefore, you have a heat transport. Okay. Now, if you use some method to measure the thermal conductivity of this particular film. Okay. So, in a classical case, how do you measure thermal conductivity is, the fixed temperatures, okay, you measure the heat flux, okay, by using the Fourier's heat conduction equation, then you extract the thermal conductivity. Okay. So, that means the heat transfer rate q dot is equal to k times the surface area times T1 minus T2 upon L, where L is the thickness of this film. So, usually we will be supplying this q dot with some kind of an external power source. So, we will know the exact amount of q dot supplied. We will be measuring temperature at the source where we supply q dot and the other end is fixed at a given constant temperature T2. From this we calculate k. So, this is the classical way of measuring thermal conductivity. So, this is a steady state method. There are also transient methods to do this. However, what happens is, if according to this particular example, whatever may be the thickness of the film, the temperature gradient in this particular case is fixed, okay, for a given value of q dot. Okay. So, if you increase your q dot, your temperature gradient will correspondingly go up, such that your thermal conductivity will always remain a constant value, right. So, that is a classical measurement, but surprisingly when you use another methods, there are several other methods apart from the classical method where you do not measure temperature directly, okay, but you actually measure some kind of a pseudo temperature. Okay. So, there are several methods. One of the most commonly used method is called 3 omega technique. Okay. So, you pass some kind of a voltage at a frequency omega, AC current, and then you extract the third harmonic or 3 times omega component of this particular voltage, and if you plug in into a transient heat conduction equation, we can show that this third harmonic is directly a function of your temperature rise across this film, which is a function of the thermal conductivity. So, you can measure this indirectly. Okay. So, if you do that and you plot the thermal conductivity as a function of L. Okay. So, suppose your L is of the order of 1000 nanometer here, okay, and something like 100, and you go to 10, and then somewhere it is 1 nanometer. Okay. So, you find that the value of k will be somewhat close to the bulk value here, because this is where there are no microscale or nanoscale effects. Okay. Your mean free path, for example, if you take the case of silicon, will be of the order of 100 nanometers. So, at this particular point the Knudsen number will be 0.1 or less. Okay. So, this value will approach the macro scale value of thermal conductivity, and surprisingly as you keep reducing, you will find that this value keeps also dropping, which is not a characteristic of bulk materials, right. In bulk materials, thermal conductivity is a constant value, right. So, but if you use this 3 omega technique, you will find that you will see that the thermal conductivity keeps dropping with reducing thickness. And finally, what happens if you go the what is the order of wavelength of phonons in silicon? Do you remember the order of wavelength? 1 about 1 nanometer. Okay. So, when you drop you reduce your film thickness to less than 10 nanometer, now the wave effects will start appearing. Okay. And surprisingly, this thermal conductivity which was dropping now will slowly start increasing again. So, this is a kind of a peculiar behavior that we will observe. Okay. Now, what is happening in this regime? It is all bulk or continuum transport, right. So, this in this particular regime we use the Fourier's heat conduction equation to estimate thermal conductivity. So, this is the validity, this is the regime where Fourier's equation is valid. Now, if you take a length scale between 10 nanometers up to a few hundred nanometers, so this is where your size effect starts appearing, that is thermal conductivity is a function of the thickness. So, this is where your nanoscale effects. So, why this drop is happening here? We will see this a little bit later in the lecture, but to give you a picture, as your size becomes smaller than your mean free path. So, now you have fewer energy carriers within the bulk of the material. So, there will be chance that more of these energy carriers are colliding with the boundaries, right, than with each other. So, the diffusion will be very negligible compared to the scattering at the boundaries. So, boundary scattering becomes the most dominant mechanism at nanoscales. So, in this case therefore, there will be a lot of temperature jump created at boundaries, because the boundaries are the sources of now non-equilibrium. Okay, you are fixing the temperature at the boundaries, but this is not what the actual temperature of the energy carriers are, because the energy carriers do not have enough number density to sense this temperature at the boundaries, because this temperature can be sensed only through diffusion process. And since you have only a very few energy carriers left, they directly come and hit the boundary and then realize this boundary is at this temperature, but by the time it is too late, and there will be a temperature, artificial temperature jump, just like you have a shock wave. Okay. So, this is called ballistic transport. So, it is like you are firing some energy carrier from this boundary, it directly goes and hits the other boundary and then senses the temperature there. So, because of this nature, there is an artificial temperature drop. So, there is an additional boundary resistance interface, like you have an interfacial thermal resistance, you have a thermal boundary resistance because of this temperature drop, and therefore, this results in a reduction in the thermal conductivity. Okay. So, this temperature drop becomes more and more intense as you reduce the particular size, right. So, and consequently what happens below 10 nanometers. So, once wave effects start appearing, so quantum mechanical effects now will come into picture. So, this phenomena is attributed to phonon tunneling. Okay. So, this is a quantum mechanical picture, we will see that. Okay. So, this is just where instantaneously a phonon disappears and appears on the other side, and nobody knows why it appears, they attribute it to quantum mechanics, right. So, this will now reduce the thermal boundary resistance, and you see that the conductivity now starts increasing because of the transmission of phonons across these boundaries, right. So, you will see this more so if you have an interface. So, you can see this tunneling process very clearly if you have an interface of two materials. For example, you can have a germanium or silicon one side, and you can have silicon or germanium. So, you have sandwich of these two materials, and you will see the phonons can easily tunnel from one material to the other. Okay. So, they do not mind this barrier, they will be able to easily tunnel across them, and even for this kind of so combination of two films, composite films, you can see this kind of behavior of thermal conductivity rise. Okay. So, therefore, this is where we have a classical nanoscale picture. So, this is a classical nanoscale picture where we can use particle based approach, and here you have to go to wave nature, pure quantum mechanics. Do you understand? So, within the nanoscale we have two distinct regimes. So, and that is why we have to use both the mean free path as well as the wavelength to distinguish between the two. Okay. So, now I will just give you a summary of some basic nature of waves before we, because quantum mechanics is all about waves. Okay. So, I will just give a basic overview of wave characteristics. So, you should understand that in waves we have two classifications. One is called a travelling wave, and for a travelling wave the wave function could be a sinusoidal or a cosine distribution function. If you assume a sine distribution function, this wave function phi can be assumed to be sign distribution both in time and space. Okay. A travelling wave will definitely have certain characteristics over time and over space. So, over time we use the angular frequency to represent the characteristic, and over space we use the wave number, right. So, you can say minus k x, okay. X could be a vector, and then this k could become a wave vector also, okay. But right now we can assume in one dimensional space and k is a wave number, t is time and omega is the angular frequency. So, why did we use omega t minus k x and not plus k x, we will see that. Okay. So, therefore, if you look at this particular wave here, so this is nothing but 2 pi times nu, this is your linear frequency which is 1 over the time period, right, and this is your wave vector which is related to your wavelength as 2 pi by lambda, and this is your wavelength. So, if you plot this particular wave with respect to space, first let us plot it with time. So, you have a sinusoidal distribution in time, and this particular separation between the peaks is given by the time period, which is 1 over frequency, right. So, this is characteristic in time, the other in space. You can plot it over x, and you have again a sinusoidal profile here, and what is this separation between two peaks in space? Wavelength, lambda. Okay. So, this is nothing but 2 pi by k, right, k is your wave number. So, you can also have a combination of sine and cosine functions to form these waves. So, these waves could be electromagnetic waves, so electric field or magnetic field, or it could be any wave, an energy carrier, phonons, electrons, all of them can be represented by these functions. Okay. So, you can also have a complex representation of waves. So, you can for example, use e power minus I omega t minus k x. This is a complex representation of waves. So, this is nothing but, if you expand, this is a times cos omega t minus k x minus I times sine omega t minus k x, right. So, you can also represent waves like this, and sometimes rather than sines and cosines you might prefer the representation in terms of exponential functions. They might be easier to handle differentiation or integration sometimes. So, you can interchangeably use them, either trigonometric functions or exponential functions. Okay. So, now if you therefore look at this particular term, okay, omega t minus k x. So, for a fixed phase, that means a wave with a fixed phase will have the value of omega t minus k x is equal to a constant typically. Okay. So, therefore, if you differentiate this, so what do you get? What will be dx by dt? what do you get? Omega upon k. So, this dx by dt for a wave with a fixed phase, this is called the phase velocity. We represent v subscript p, phase velocity. Okay, for a constant phase plane. So, this tells you what is the speed of the propagation of the wave. Okay. So, and that is related to your ratio of angular frequency to your wave number, right. So, if therefore, if you plot therefore, a wave with a fixed phase omega t minus kx is equal to constant, you get a positive slope, which tells you that in a phase plane, if you plot phase plane of x t versus x, time on one axis and x. So, how do these waves go? In which direction do they go? So, they run on towards the right side. Okay. So, these waves you can represent them over different position and time space like this. These are all waves with positive slope. So, these are called right running waves. Right running waves, and typically their phase, fixed phase is omega t minus kx is equal to constant. So, the slope is given by the ratio of omega upon k. Similarly, if you take the waves which are omega t plus kx is equal to constant. So, there the slopes are negative. So, they will be running on the other side. So, you have these are called left running waves, omega t plus kx is equal to constant. Okay. So, these are some basics, most of you might already know this, I am just again revisiting. So, now these are all the characteristics of what we call as travelling waves, they travel in position and time. So, you can actually use two travelling waves. Okay. So, one travelling towards the right, one travelling towards the left, and create what is called as standing wave. You can superimpose one wave travelling towards the right, one wave travelling towards the left, superimpose these two, and finally, what happens, the wave now cannot move this way or this way, this will be just fixed in space. So, these are called standing waves. Okay. So, we will now look at the characteristics of standing waves. Okay. So, in standing waves typically you have a right running wave which is moving in this direction, and you have a left running wave which is moving in this direction. You see, superimpose these two, assume a linear superposition of the waves. Okay. So, the wave which is now, let us look at only the coordinate, the position space, not the time. Okay. Let us look at only position, and therefore, the right running wave will be indicated by e power I k x, left running wave will be b power minus I k x, right. So, we linearly superpose these two and we create the standing wave. So, wave function is described like this. Okay, because in the complex representation, so for the case of right running wave in spatial coordinate, it is e power I k x. Okay. So, the left running wave will have e power minus I k x. So, if you superpose these two, you create the standing wave with this particular wave function. So, this is the right running wave and this is your left running wave. So, to an observer it will look like this wave is particularly pinned and this is not moving at the edges. Suppose you confine this wave within a particular domain, for example, okay, this boundary, at the boundaries of this domain, since the domain is stationary, the wave will be appear to be pinned to these domains and it cannot move either right or left. Okay. So, the typical value of this wave function will be 0 at these boundaries. Okay. So, therefore, now if you look at a standing wave of in a particular domain. So, let us take a domain like this and you create a standing wave. Okay. You can have the standing wave might look something like this. The wave function will be 0 at the boundaries. Okay. So, now if you want to write this complex representation in terms of exponential functions, we can always convert this back to trigonometric functions. So, we can always write this also as a cos k x plus b sin k x. So, you can always flip back and forth between exponential representation and a trigonometric representation. So, let us now start with the trigonometric representation of this wave a cos k x plus b sin k x, and at the boundaries let us say x is equal to 0 and this is x is equal to capital D, where D is the length of this particular confinement, okay, which produces the standing wave, right. So, at both these boundaries the value of wave function will be equal to 0. Okay. So, now therefore, you can apply the boundary conditions. So, now you can calculate what is this, what are the constants and also the corresponding eigenvalues. So, can all of you can do this and let me know. So, therefore, what will be A? A will be 0 and therefore, your phi will be b sin k x. So, if you apply the second condition at x equal to d, okay, you have b sin k d will be 0. If b is 0, the entire solution becomes trivial. So, therefore, sin k d should be equal to 0, which means that k d should be equal to n pi. Again n cannot be 0. If n is 0, again the solution becomes trivial. So, n should be equal to 1 2 till infinity. So, therefore, your k becomes n pi by d. Okay. So, with this now we can calculate what is the energy of these waves. It could be an electron wave or a phonon wave or a photon wave, which is within this particular element of thickness d. So, what is the energy? So, if you take the particle nature, your energy is nothing but p square by 2 m, where p is your momentum, particle momentum. Now, we just convert this particle picture to wave picture. So, how is p related to the wave number? H bar k is p. You have seen this in the last class. So, therefore, the whole square divided by 2 m. So, now we got the expression for k as n pi by d. Okay. You can substitute into this and you will be getting the expression. This is, if you rewrite in terms of just normal Planck's constant, we have h square by 8 m into n by d the whole square. So, I am just plugging in for k what we got from there into this. Is it clear? So, now if you represent therefore different modes of these waves, okay, if your n is equal to 1, how does this wave appear? So, let us draw the confinement, and this is your separation distance d. If your n is equal to 1, so in this case k is equal to pi by d. So, how will the wave look? This is how the standing wave will look. Okay. Now, if n is equal to 2, your wave number will become 2 pi by d. So, you will have therefore a peak and a trough. Okay. So, similarly, if n is equal to 3, 4, so you have multiple modes, n is equal to 1 to infinity. So, all these possible waves are there, all these possibilities exist for the standing wave. Okay. So, once you put the standing wave within a particular confinement, this wave now appears to be discretized into infinite number of waves of different modes. So, infinite number of standing waves are created within this particular confinement, okay, and each of this will have a particular energy, and that energy is given by this expression. Therefore, what is the discretization of the energy levels between n equal to 1 and n equal to 2, 2 to 3, 3 to 4 and so on, that is the delta E. The delta E is now given by h square by 8 m delta n by d the whole square, right. So, therefore, if you take the case of electron, yeah, but h is a constant, m is a constant, d is a constant. So, the delta is only due to the delta in n. Delta of n square, yeah, that is true. So, you mean you want this to be written, okay, I take the d square out like this, right. So, now let us take the case of electron. So, we will call this mass associated mass of electron. Okay, we want to see what is the jump in the energy levels between two successive modes. Okay. So, ME will be equal to 9.1 10 power minus 31 kgs, Planck's constant H is 6.6 into 10 power minus 34. Let us take the example of a confinement which is 1 millimeter, okay, and let us take delta n to be equal to 1, jump in the energy level. Okay. So, what do you get for delta E? If you substitute this, can somebody check that? We want to now look at the jump in energy level from one mode to the second mode. Yeah. So, it should be actually delta of n square, right.
Delta n square is a 1?
Yes, should be delta n the whole square. Okay. So, the delta n is basically in this case unity. Okay. We want to look at the change in the energy between 0 to 1 or 1 to 2, not 0. Huh?
1 to 2 is not delta n square.
It should be
4 minus 1.
yeah 4, no, that's what it should be in this case. Yeah, I think no, this cannot be delta of n square for sure. If you then look at yeah 2 to 1, then it is okay. Then if you, then this is 4 minus 1, yeah. Yeah, for example, let us go from 2 to 1, then you can calculate and let me know. Okay. So, this will be therefore 4 minus 1, right. So, let us say 2 to 1. So, what do you get?
Cross 10 is to 31.
1.8, 1.79 into 10 to the minus
1.79,
13.
just a moment, 1.7 into 10 to the power minus 31. Okay. Okay, this is in joules. Okay. And now, what is the energy associated with room temperature, for example? So, that is your Kb times T, where Kb is your Boltzmann constant. So, this at room temperature comes out to be 4.1 into 10 power minus 21 joules. Okay. So, what this means is, if your order of D is around 1 mm. So, your delta E, that is the difference between the energy levels due to this quantization, due to the discreteness, will be less than your discernible energy, because your normal energy level at room temperature itself is 10 power minus 21, and this is much smaller than that, right. So, you cannot even sense it, you cannot even feel these subtle shifts in the energy due to the quantization at room temperature. Okay. Whereas, if you now put your D to the order of nanometers, okay, let us calculate the same thing with D as 1 into 10 power minus 8 meters, 10 nanometers. What happens? What happens to delta E? Okay. So, this we have d square in the denominator now. So, as your d is reducing, that should increase as 1 over d square. So, this goes to 10 power how much? Minus 21. So, now you see that the order of delta E is comparable to kBT. So, now you can really go and measure the change in energy level from mode n equal to 1 to n equal to 2, and these are significant values compared to kBt. So, it depends on what is the size of this confinement you are looking at. If your confinement size is very large, then the shift in the or the spacing between these energy levels are so small that you can almost neglect the discreteness or quantization. Whereas, if your confinement length becomes smaller and smaller, this shift becomes very large, and therefore, the real quantization happens. Okay. So, all waves in principle have some discreteness even at room temperature, but it depends on the size of the confinement. We are talking about waves maybe which are of the order of nanometer confinement. So, there it becomes very significant, whereas if you are talking about millimeters, centimeters, there you can completely ignore these quantum effects. Okay. So, this is a very nice simple example to illustrate what happens to a standing wave in a confinement and what happens to the shift in energy levels when the confinement size reduces. Okay. So, I think this expression what we have derived for energy, you have to just mark it, because the way we have derived now is very less rigorous. We have just used simple wave equation and then we have derived this E. But now next what we will do, now we will introduce Schrödinger's wave equation. Okay. So, that is more rigorous for describing quantum mechanical waves, and from there we will also derive for a simple confinement, and we will see that the expression comes out to be the same. Okay. But we will do it in a more rigorous way using the Schrödinger's equation. Okay. So, we may not have much time to solve anything today, but I will at least introduce you the mathematical description of the Schrödinger's equation. Okay. So, in fact, so when Schrödinger first when he first described these wave nature through this particular equation, so he did not understand the meaning of the wave function. Okay. So, he wrote the mathematical form of this wave function as minus modified Planck's constant h squared by 2 m times Laplacian of wave function psi. Okay. So, we will call this as psi to say that this is a wave function, we will see what it is, plus you have a potential energy constraint u times wave function, which is equal to I modified Planck's constant times d psi by dt. So, this is your Schrödinger's wave equation. Okay. So, generally what people do is they use an operator called the Hamiltonian operator. Okay. Hamiltonian. Okay. They use this operator H to signify this entire term minus modified Planck's constant square by 2 m del square plus u. This entire operator is called a Hamiltonian operator. Okay. And they write this in a very compact form, therefore, as H psi is equal to I h bar d psi by dt. Okay. We will see what is this Hamiltonian, and this is actually the indicator of the energy possessed by the particular wave. We will see that. Okay. But right now we will just state it, later on we will prove that this is nothing but the indicator of the energy possessed by the wave. Okay. So, Schrödinger basically stated the wave characteristic like this. So, this is it could be this psi could be a wave function which indicates either a pressure wave for example, or a electric field, it could be anything. If you are talking about electron, this is a basically electric field wave, it could be pressure waves, molecules, pressure waves. So, whatever field that you consider, so this is the corresponding wave function for that. Okay. So, therefore, the first term here, this is a Laplacian operator in space, and this is a function of only the space, whereas the second operator here, it is the potential energy constraint. And this is your temporal derivative. So, that is your wave function is a function of both position and time, right. So, this is a partial differential equation. Now, you can compare this, for example, if your potential energy constraint is 0, if there is no potential energy constraint, okay, the particle is say or the wave is free to move without any constraint on the potential energy. So, that means u is 0, and therefore, the equation will be minus h bar square upon 2 m del square psi equal to I h bar d psi by dt. Now, compare this to your energy equation that we derived. So, how does your macroscopic energy equation look for conduction? You have k into del square T is equal to rho c into dt by dt. So, it looks like a similar structure, right. What is the mathematical nature of this heat conduction equation here? This is parabolic because of the temporal derivative. If there was no temporal derivative, it would be elliptic equation. This is governed only by the boundary conditions. Now, it is governed by also the initial condition. So, it becomes a parabolic equation. You see structurally this looks similar if your h square by 2 m is replaced with k and this by rho c. But what is the nature of this wave equation? This is called hyperbolic equation. That is why it is a wave equation. Any wave equation is hyperbolic. Okay. So, what is bringing this hyperbolic nature is this imaginary number I. Okay. If there was no imaginary number, this equation would be parabolic, right. So, what brings the hyperbolic nature to the Schrödinger's equation is essentially this imaginary number. Without it, it is not a wave equation. Okay. So, basically what is interesting in history is that Schrödinger himself did not come up with a correct explanation for this wave function psi. He did not understand what to do with the solution for psi. So, later on it was Born, BORN. So, this scientist, he understood that there is a significance to this wave function only if you multiply the complex conjugate of this wave function. I denote the complex conjugate as psi superscript star. For example, if psi is equal to a plus ib, the complex conjugate will be a minus ib. Okay. And if I take the product of this complex conjugate of the wave function and this, then together this product is nothing but the probability density function of finding a particle at some position in space, of finding a particle at a location in space. Okay. So, by itself the wave function does not have any physical meaning, but if you take the product of complex conjugate of the wave function with the wave function. So, this gives the probability of finding a particle at some location, and if there is a particle, it has to be found somewhere. So, therefore, according to the normalization, what should happen between the space 0 to infinity, the product of psi star psi should be equal to 1, because the particle has to, if there was a particle, it has to be found somewhere in the infinite space. Okay. So, therefore, this condition has to be satisfied. This is called normalization condition. So, this should be minus infinity to plus infinity, because the space you do not have coordinate system 0 to infinity, there it is minus infinity all the way to infinity, normalization. Okay. So, this now Bond brought out the proper way of interpreting the solution. So, with this we can actually find out important things, like for example, the exact coordinate of a particle. Okay. By using this we can find out any expected value. Now, in quantum mechanics everything is an expectation, nothing is 100% sure. So, we always use an operator like this to show that this is an expected value. So, the expected value of position, okay, for example, is denoted by this particular operator R, okay, is nothing but minus infinity to infinity psi star R psi. So, based on this operator you can find out what is the probable location where the or expected location or expected coordinate of this particular particle. Similarly, you can do that for momentum and energy. So, we will continue that tomorrow. Okay, we will see what are the operators for momentum and energy. Okay.